Welcome to the AgEmerge podcast, brought to you by Ag Solutions Network. Your farming challenges are unique, so your practices should be too. We're here to share emerging ideas, build connections, and provoke conversation.
Get ready to improve your soil, your crops, your livestock, and your family's livelihood. I'm your producer, Kim Chase.
And I'm your host, Monty Bottens. Thanks for joining us.
Thanks for joining us. Today, we welcome Dr. Dan Rooney, founder and CEO of LandScan. Monty talks with Dan about his journey spanning decades in soil science, ag tech, and how he and his team are revolutionizing how farmers understand and manage their land through advanced soil probes and digital twin technology. Get ready for an insightful conversation about the future of farming, precision agriculture, and sustainable practices. Let's jump right in.
Welcome, everyone, to this episode of the AgEmerge podcast. Today, I'm joined by Dr. Dan Rooney, founder and CEO of LandScan. Welcome, Dan. How are you today?
I'm excellent. Great to be here. Thank you.
Dan is currently out in California and has done some really amazing work. And I'm going to let you share your story. And we're going to have a lot of things to unpack and some great technologies that build upon each other. But Dan, tell us your story and how you got involved in agriculture and technology and where that's led to today.
Yeah, well, that's I'd have to go quite a ways back for that, but let's see. I think the spark, I would say, for what we're doing today really started all the way back in the mid 1990s when I was getting my master's degree at Texas A&M, and my master's is in soil physics, and I had to teach the soil physics lab for several semesters. And we were doing tests, some of them outdoors, some of them in labs, things like hydraulic conductivity, soil texture, bulk density, a lot of the things that are relevant to soil health, for example. And I was always amazed at how different everybody's results were. This is the graduate level, senior level course. Great equipment. Everyone's being very meticulous. I would do the lab on Sunday night, and I had 2 sessions during the week. And I just saw a lot of variability. And so that always stuck with me. I ended up getting a job after that in the geotechnical industry at the dawn of what was called what is still called cone penetrometer technology, or CPT. And in the mid-90s, the company I was hired by was pioneering electrical CPT. So these were sensors. There were 2 sensors and a probe that was pushed, maybe 100 feet or so into the ground, and a little bit over an inch a second down. So they were looking for stabilized soils for construction, tunnels, bridges, skyscrapers, and trying to define the soil properties. But they were going down so deep, and it took so long that they might get 1 or 2 or 3 of these in a day. And within a couple of weeks of being there, these were all civil, mechanical, and electrical engineers working for this company. And my background in soil physics, I took a lot more soil chemistry, soil microbiology, and things of that nature. And I suggested that we might come up with additional sensors to measure chemical properties and other contaminants and things that are in the soil. And so pretty quickly, I developed a redox pH sensor. We started doing development of fiber optic sensors with spectrometers looking for oil contamination. And so what happened was, now instead of going down 100 feet to do geoenvironmental applications, you might only be going down 10 or 20 feet. So now in a day, you don't get 3, you might get 10 or 15 or 20 of these. Now all of a sudden we could map a plume, right? So because we took enough of them, we could do a transect across a plume, find out where it was more intense, at what depth, and the extent of it. And that really changed the geoenvironmental industry. So after about 3 years, I realized, what if you were only going down 5 feet? All of a sudden you can collect so much information in a day. You would change the way people map soils in the near surface. So Anyway, the company wasn't interested in going that far, out of their comfort zone. And I ended up going back and getting my PhD at University of Wisconsin in remote sensing, but miniaturized the geotechnical sensors. And at the time, this was the late 90s in agriculture. Soil was still being mapped the old-fashioned way, if you will. There was a penetrometer that some of your listeners may be familiar with, but it's a very pointy tip, 30-degree tip, pushed in the ground. But it was not able to measure all of the different or very many different properties with depth. And so anyway, I ended up converting some of the engineering technology into the soil space, also developed a miniature camera system, and spent a few years around the Midwest collecting data for this research. And then it was late 1999. And what would happen was I would go into the field and I would push the probe in the ground. I could see the data profiles that were being collected at the time. And I got to where I could predict, because what else are you going to do all day? You're out there, in collecting soil data. I got to where I could predict what those profiles were going to look like before I pushed the probe in the ground based on where I was on the landscape, because I'd done it so much and I got good at that. So what I would have to do is I'd have to put a flag in the ground. So this is 1999 now at the end of it. And I would have to check out the GPS system from the university. I'd take pictures, write up a report. It was a security issue. And I was done with my coursework. It was the very end of my research. I was standing, it was late November, the sun's going down outside of Madison, Wisconsin somewhere. I'm looking at a field of orange flags that I have to come back to when I can get the GPS in 10 days or 2 weeks. And I hear on the radio that we're going to get 2 feet of snow over the weekend. And I realized, oh no, I'm never going to see those flags until spring, if then. And I need to finish and need to get a job and blah, 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 all that. So I was very stressed out at that instant. And the next story on the radio was, in May of next year, we're going to allow GPS for commercial use. At that moment, I had an idea and I knew. And from that point on, I started doing what I'm doing now. I knew I could develop software that would integrate the GPS in real time, process the data in real time, and you could use those in combination to make a more efficient three-dimensional map. Started my company the next week, the first company doing this. And within a couple months, we had a global license with John Deere. We were part of an ecosystem where we provided the soil data. There was another company provided weather data. Another company provided airborne remote sensing. And we went around, we were mapping around the world as part of this ecosystem with John Deere. There was a model, decision support model at the core, called Precision Agriculture Landscape Modeling Simulation. It's Palm's model, developed out of University of Wisconsin. And we did that until 2008, when the economy crashed and John Deere, like a lot of companies, went back to what they did best. And for them, that was, making tractors, broadly speaking. And so they got out of this industry, the ag information type industry. And I had negotiated that any improvements or advancements in this technology, I could acquire back just for the depreciated cost of the equipment, which I did, and took systems that were in China and Europe, all over North America, some in South America, and brought them all back to Northern California and started focusing on vineyards and orchards and other high value crops. And then at that point, we were providing these services. And, when we were doing the remote sensing with Deere with an airborne remote sensing platform, we were mostly flying over corn, soybean, wheat, late season. So you have closed canopy. And so in satellite remote sensing, back when I was doing my research, I also taught the remote sensing image processing lab at Wisconsin. We were using large pixels, Landsat, 30-meter pixels. And so all these remote sensing techniques were developed around a calibrated pixel that was covering a closed canopy. So in the mid 2000s, when we were part of the DEER program, we had airborne remote sensing, but they were still looking down at a closed canopy. So now instead of a 30-meter pixel, you got a 2-foot pixel or whatever, right? But you could still be lazy and apply those same techniques that you did with satellites. So it worked out. But now it's 2010 and the airplanes are coming to California. And I was at a meeting at UC Davis, and they had just tested some imagery from airborne systems, and they were like, we can't use it. It's too noisy. And I was like, I know why it's too noisy. And it seems obvious now in 2025, but in 2010, it wasn't. So we developed the world's first software for analyzing airborne remote sensing called PurePixel. And PurePixel was it extracted the pixels that were on the canopy and differentiated them from those that were hovering, straddling shade, cover crop, soil, whatever else. And it made the analytics pop. So now we had the soil information system technology, which is what we called the soil technology, and we had PurePixel. And we were deploying those and combining them after the fact, after they were collected in what we called ag forensics. And so then late 2013, my company was acquired by Trimble, and I and my team now became indentured to Trimble for 5 years. And so we're now back out at 6 continents mapping the soil information system and PurePixel technology. We were part of that ride, making sure that everything went smoothly, which it did. But now year 4 comes along, and I was saying to Trimble, hey, look, number one, the soil information system technology that we're deploying on 6 continents is unchanged from my PhD 20 years ago. Same hardware, same software. We can put new sensors in here now to measure different things. We were just measuring physical properties, moisture, plant available water holding capacity, texture, density, important things. We weren't going after any nutrients or any other,
All you had was pH at the time, right?
we didn't have pH.
Oh, okay.
We were doing physical properties with
Okay.
the probe.
Okay.
So moisture, salinity, density, texture, water holding capacity,
Okay.
all of those things. Then we would sample for nutrients in a targeted way
Sure.
based on the physical properties, but it was still an indirect
Cool.
measurement because sensing technology hadn't been advanced 20 years ago, or at least something you can make small, right? These were small, you'd have to go, measure in the ground. So, so that was one thing. And then the other thing, the drones are coming, right? So it's 2017. And just like we had this opportunity from satellites to airplanes, we were going to have an opportunity from airplanes and satellites to drones and do things that you can't do with the other options. So anyway, 5 years was up. I left amicably and started LandScan. And we were on stealth for several years. I was able to hire all of my engineers, scientists, software developers that had built these systems that we've deployed on 6 continents over the last 20 plus years. Many of my senior staff, the engineers and scientists and developers, were part of the exit to Trimble, and that was a significant event in everybody's life. And so they were easy to bring on again because they knew that it was successful last time, and why wouldn't it be this time? And there were so many opportunities to make better systems than we'd been using. So anyway, that's how it all. It's a long story, I realize, but it gets you kind of the background and sort of the motivations of what we're doing today.
Well, a couple comments from my perspective. First off, I think there's a lot of times large companies get excited about startups, and oh, it's a cool shiny object, and we want to bring it into our ecosystem. And then they just don't understand what the value of it is, don't take full advantage of it, don't invest in it. And then when, like you said, you face bad times, or in Trimble's case, they've um, they Trimble is just kind of in an odd spot. They've just kind of lost their way on what they were doing, and it's interesting to see that kind of the ebb and flow that happens in those big corporations. So congratulations to you to bring that back. You've it's been basically three startups for you, if you will, the same product but three times, right? And
Right.
congratulations on that. And because it's a really valuable tool, or really a system of tools that you've assembled. So hard to do it, hard enough to do it once, let alone three times, Dan.
Well, the technology keeps advancing that drives it.
Right.
It's a concept,
Mhm.
this digital twin concept,
Hold
that,
hold on just a second. We don't want to go there just yet. That's too much fun. We got to save something for the end, Dan.
all right, good, very
But no,
well,
one thing I did want to insert in there, the pure pixel thing. Uh, Talk to us about that, because we started about that same time. I think it was 2011, 2013. We started doing aerial imaging, and our whole it was our Crop Commander platform is what we called it at California Ag Solutions, and we had drones. We just couldn't get the acreage coverage with drones, and then we did fixed wing aircraft. And, I remember we had liquid cooled CPUs and all this stuff trying to process this data, because what our ultimate goal was to identify change over time. So we understand that every field is variable. Great. We want to know, is that variability changing? Is the bad spot getting worse? Is the good spot getting better? What is changing week to week? And it was so frustrating because the irrigation and the shadows, like you talked about, high altitude clouds, thin clouds, thick clouds, moisture levels, temperature levels, time of day. There's so many things that go into imagery that people do not take an account for. And we spent a lot of money on software and people and propeller heads to make this happen. And eventually we got to the point where, like, okay, we're learning nothing here. I want a plane to go up and fly the same field all day long for like a week. And just, there was more variance in 20 minutes sometimes than there was in a week. And
that's right.
angle of attack, direction of travel, cloud cover. It's frustrating. How did you overcome all of that and to get that? Because that is a key component to get good images. And there's a lot of bad imagery out there. So talk to us about that pure pixel process.
Well, sure. Well, so the pure pixel was the second generation.
Hmm.
Now we've moved past that. But the pure pixel itself was simply an extraction of the pixels that were relevant,
Hmm.
right? That were on the canopy, and so we developed software to be able to do that. But what we do now is we're calibrating the imagery. And all of the principles of remote sensing, for the most part, are derived from satellite applications. And satellites are calibrated. We have the calibration factors. They obviously have to go through the atmosphere, and that's important. Now, one of the things that LandScan does differently than I think maybe anybody else is that when it comes to satellite data, we don't take the satellite data that's sold from the platforms. We take the raw satellite data
Hmm.
so that we are able to put custom atmospheric and land use filtering calibrations into them. So right from the very beginning, if you compare our same imagery from the same satellite to a competitor's, ours is going to be cleaner. It's like lowering the water level so more islands stick up, right? And so right from the beginning, we're starting to reduce the noise.
Hmm.
Airplanes, I think there's a place for airborne applications, but I actually believe that airplanes are going to be spit out like a watermelon seed by drones and satellites, because we're right now using high resolution satellite imagery that's down to a foot pixels.
Yep.
And we can get a lot of pixels on a canopy of a almond tree or pistachio or something like that. But calibrating with the drones is something else that others are not doing. And the temporal analytics you're talking about, the reason those are frustrating, not only what you said, the clouds and the variances by sun angles and all of that, but the calibration factors, you get one calibration that's applied to the whole field. So when you come back next week or whenever the next time frame is, the reality is that all things were changing non-linearly within the field. They don't all have one calibration factor cannot be applied to the whole field. What happens is every time you come back, it gets noisier and noisier because there's drifting in different information dimensions and you're only using one. So what we do is we actually have calibration panels that we put out in the field when we fly our drone data. And we've developed the software to be able to do this very quickly and efficiently at a large scale, so that we're not only collecting and calibrating the spectral data at the pixel level, so that we're getting ready, lowering the noise level. Again, seeing more islands of information sticking up, lowering the noise level. We also are doing photogrammetry, which nobody else is doing, right? LiDAR will eventually get there, but LiDAR is still too clunky to do at any sort of scale at the drone level. So we actually have control panels. We're actually doing engineering quality drone data. We're getting canopy volume, height, leaf area index. We're getting all these metrics about the canopy that we use to analyze the crop so that we can then go in and investigate what is it that's causing that variability. And we do that on the soil side, which we can talk about
Yeah.
next.
No, that's fantastic. I love the idea of putting those essentially, truthing pads out there to where you can. That solves a lot of issues.
If you
And
don't do that,
technology today is so much better with satellite. We didn't have that 10, 12 years ago, the
absolutely.
foot pixels.
That's
So,
right. That's right. That's why we keep reinventing these systems, because you're getting new inputs,
yeah,
satellites to airplanes to drones, right? And that's why.
yeah.
The AgEmerge podcast is brought to you by Ag Solutions Network. The ASN team is hands-on, digging in and invested in regenerative agriculture. Along with the proper plant nutrition and biologicals to boost your soil microbiome, we provide the ideas and implementation guidance to support you on your soil health journey. So stop farming the same way and contact Ag Solutions Network today at asn.farm.
So, you're really looking at the crop, from underneath and structurally, like you said, you're getting a full application of that. So, um, let's dive into the digital twins. I think this is unique. My understanding of it is you're doing all of the sensor arrays that you've developed or partnered with, and all of your internal information there. And essentially, you can create a model of, let's just pick on a tree today, and then you can create that in a digital space and almost run scenarios on it, correct? As far as weather scenarios, fertility, irrigation, and 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 just say and unleash AI on that uh, to, hey, optimize. Um, Walk us through this. This is amazing.
Right. Yeah. So, the concept of a digital twin has been around for a while. I mean, often the first use of a digital twin is pointed to the Apollo 13 mission. And it was because we had an exact replica of the hardware and the software that they were operating on out in space, that they were able to ask them to try this and try that and run these different tests. We would run the tests back in Houston and send it up. But in agriculture, this concept hasn't been around, and we were the first to apply this type of approach to agriculture. But in order for it to work, you actually have to have an exact, at the appropriate scale, digital representation of your field. And I just talked about the remote sensing side and how we are able to, through calibrated analytical quality imagery, get a picture, right? In a sense, all sorts of different data signatures. We call it the digital vegetation signature of the canopy. So there's a concept that's been around in agriculture for a long time called the gem analysis. And that is that the performance of a crop is going to be a function of three things: the genetics, the environment that it's growing in, and the management. So we know what the genetics are because we've planted the crop. We know what the management is. So what we do with the remote sensing is we get a digital proxy for how the crop is performing in all those different dimensions. And sometimes that you care about quality, sometimes you care about yield, sometimes you care about different aspects of it, but it doesn't matter. You have a digital proxy for the canopy. We know the G, we know the M. So we go around with what we call the digital soil core, and we solve for E. So the digital soil core is a probe. It's an evolution of the technology I described before. It's pushed in, pulls out, takes about 60 seconds to get information down to about 4 feet in the soil. We have 7 sensors in there. We have the same sensors we were using before for the physical properties, but we also added a imagery, a camera. So we have high resolution imagery. We have a spectrometer, so we're getting laboratory quality analytics. We have an acoustic sensor, which is listening to the grinding, crunching, and scraping as the probe is inserted into the ground. So all of these 7 different sensors are giving us, when we push the probe in the ground, thousands of measurements per inch. They're objective. All those sensors are calibrated, engineering calibrated. So we immediately get a scan of hundreds of thousands of independent measurements of the soil right under a tree or a vine or any place you visit. So what we do is we'll scan the field and we'll say, okay, let's create 5 classes of vegetation. 1 being the best and 5 being the worst, based on whatever the objectives are of the grower. And we might go to 8 trees, since we're picking on trees. We might go to 8 trees in each of those 5 classes. And we push the digital soil core in right under that tree. And what happens is now we have a digital soil signature of the profile in a way that's not possible. And this is one of the main differentiators. It's not possible if you're taking soil samples. Soil samples, laboratory sample analysis is the wrong reference. Like we use a term in cartography, datum, right? It's a reference point. The datum for elevation is if you're talking about flood, you want to know the sea level, your elevation with respect to sea level. But if you're flying a plane, you want to know the elevation relative to the mountain, right? If you're just looking at the sea level, you're going to crash into the mountain. So different datums, different references are important for different applications. Mm-hmm. And it's impossible to collect enough soil data through samples to make a statistically accurate map. There's too much subjectivity, there's too much variability, and there's too much error along the way. And so anytime you have to have a soil sample, you're breaking the circuit of analytics. AI is not possible because you have too much subjectivity and lack of information and spatial resolution. Mm-hmm. So in this way, by pushing this digital soil core in the ground, we're getting all of these measurements of the soil environment and attributes like depth and thickness and sequencing and all of these things that aren't taken into account mm-hmm. when you're doing these very coarse, non-informative soil samples. And so this together, the digital vegetation signature combined with that digital soil information is a brand new way of doing things. And that's that digital twin. And it allows us to do things like, hey, I understand that 2 parts of your field have water stress. The crop is of water stress. But what you don't know without our information is that more water over there isn't going to help because there's something else that's limiting the yield first, right? And so without that dimensionality, you can't really optimize your management. You're just stuck with a one-size-fits-all.
So by using essentially the advanced imaging technology you're identifying those zones in the field that are, statistically different, within dividing it into 5, like you were saying, then take samples within, the top uh, fifth and the second fifth, and to identify what is driving that. Then you can see what those environmental factors are. My question is then you're solving for E that way, like you said, in the gem process.
Yep.
Then by solving that, the only other lever we really have to pull is the M.
That's the
But
lever.
so
That's
now,
exactly what we're doing. So now we say,
yep.
hey, okay, now we know what to do to adjust the M or whether it's economic. And so we have the layer of analysis includes what does it cost
Hmm.
to do? What are the input costs? What are the management costs? What's the potential? So we've created one of our unique outputs is the output potential of a field.
Hmm.
And so the agronomist can go in and then interact with our software and say, you know what? I can't change that, or I won't change that
Right.
about that part of the field. And therefore, our recommendation takes that into account. And it really is a whole nother level of optimization that's been not previously available. One of the things that I think, and I think your audience might appreciate this, is that when I going back again to 2000 when GPS became commercially available, I was in Wisconsin and I saw everybody put a GPS on their harvester and everybody had a yield map. And so now you could go to places in the field because you saw the distribution, the histogram
Hmm.
of the distribution of yield. You could go to places in the field and investigate them. But in permanent crops, we don't have yield maps. So there is no distribution. I got 2,600 pounds an acre off of my 80 acres. And you might know where it's really bad, but you don't know where that 10th, 20th, 30th, 40th percentile is. And that's why we do what we do, because then you can go in to that 20th to 50th percentile and tweak the M, because the M is optimized. The one size fits all M for that field is optimized for the part that's the 60th, 70th, 80th, 90th percentile.
Hmm.
But you don't know where that's happening. You don't know what levers need to be pulled or could be pulled. And that's what that digital twin allows.
And I think I'm a farmer in the Midwest, and when we first got that first yield monitor, I remember back in '96 or something. We first got it. We didn't have the RTK correction, obviously,
Sure.
but what we couldn't believe was how much of a variance there was. We knew there was variance in the field, but we didn't have that histogram, that bell curve distribution where the yields are at.
Yep.
And what we thought was maybe a 10 to 20% variance was 40 to 60%. And it was really mind-blowing when that first came out. So, now you can see where that variance is at by your canopy observations. You can say, hey, there's a cleach layer at 3 feet. You're not going to change that, you know, or there's this is going to take 10 tons of sulfur to correct this sodium carbonate problem. That you economically can't do that. um,
Right.
and you can make those decisions. So now this is I just love how your technology and the pursuit that you've done with you and your team, Dan, has just built one on top of another, and it just keeps coming. But two things. One is I was thinking I really see a play where you get all that good information and there's so much to analyze within there that I think there is an application for AI with that good information to help us know as agronomists or farmers what levers we should be pulling, and if it is economically feasible to pull those levers as we gain more and more information. I think that's one future outcome of what you're looking at. But the other outcome, I think, and I'll let you take it away from here, is in California, especially, we have farmed based on never historically we have not farmed based on a lack of water. Okay, we have farmed based on a lack of sunlight. How many trees can you put in per acre? We got to leave a wide enough spot for a tractor to get through. But man, we're going to jam it to it because we're going to put 4 and 5 feet of water out there, and that's it. Now all of a sudden, whoa, we can only put a foot and a half of water on this field. And you've got your histogram distribution that you found, and you know that, hey, this 20, there's 20% of this field, there's 5 acres over there, 10 here, two there. I don't care what you do, you're wasting water putting on this. We just need to stop. that. We need to get the chainsaw out and do that. The second distribution, we need to get out and thin it by half. But or maybe we just need to say, hey, here's one good spot in this field that's going to be very water use efficient, highly productive. That's where we need to farm and fallow the rest. So Sigma is going to really play into this decision making matrix. And so there's this combination of water scarcity and I think more informed decision making when you're looking at hundreds of thousands of data points. How do you see that all coming together and shaping the future of farming in California?
Well, yeah, absolutely. So your first point, it's not a future, it's a current. So we call our digital twin root cause analytics,
Yes.
and it does what you described, that we are doing the AI. There's
Cool.
the concept of AI is overused, to say the least.
It's
And in
it's a buzzword.
agriculture, it's a buzzword, but it's and I mentioned before, if you don't have
It is.
accurate soil information, you cannot run AI. It's not possible. It breaks the circuit. So we are uniquely able to run these types of AI analysis. And we do take into account, as I said, what does it cost? The agronomists then can interact with our software and make those decisions. The analysis reruns in a matter of seconds, and it shows them the parts of the field that are a loss and the parts of the field that could be resuscitated, or you just accept their current level. You have a low pH at a foot down, and you're not going to remedy that. So quit adding nutrients because it's not going to be taken up. Right. So those kinds of that, or I can add more lime to that part of the field if I'm managing my soil pH in a vacuum. But I'm not managing my soil pH in a vacuum. I'm managing that part of the field where there's other yield limiting factors that I cannot address. And so I'm not going to put more lime. So we produce output maps, return on the variable application rate maps that go right into a variable spreader that can put the right amount of lime, the right amount of gypsum, the right amount of SOP out as you go through that field. And some parts of the field, if you were going to put 2 tons on, it's always the case that we see that some parts could use 4. Some parts don't need any. Some parts need 2. It's usually 10 to 20% of that field actually needs the amount that you're going to put on in that one size fits all. And you see a return on investment instantly from our services. Because if you're putting if you don't know how to adjust the M in the gem, you're managing for the lowest common denominator, and it's wasteful. And you're just not, as you said, it's an opportunity cost too. It's not just a cost of inputs. It's a yield impact because the parts of the field that could use 4 tons aren't getting it, and they're not living up to their potential. So you're taking a hit on the yield, and then you're also taking a hit on opportunity cost, as you described, because you shouldn't even be farming this part of the field. Use that water, use those inputs somewhere else that you have the potential to extract more value.
And I think, let's say we're starting with a field and let's just describe a field of the future. And we do have these water limitations, for easy, a quarter, 160 acre field. And we know that we can effectively get, water. We have enough water to produce a permanent crop on a third of the acres in that field. I mean, you can go out there. Can you even use like a annual crop to determine where the soil zones would be based on how the crop grows or not in order to do your vertical probes in order to prep for a permanent planting?
Yeah, so with an annual crop, you're going to be able to go back and look at historical remote sensing data.
Hmm.
You can get Sentinel data going back to 2017 every 5 days, and then you're going to have clouds, but our software sucks all that in, filters it out, and removes the data that's not good,
Hmm.
and produces zones. And then those zones, and you can tweak them. Look, I just care about July 1st to August 15th or whatever. You can put those metrics in there to hone in on making zones that are relevant and then go and investigate them. And in an annual crop, you're going to investigate at a different scale than you would investigate it in a permanent crop. So the cost is going to be lower
Mhm.
because the cost of implementing the solution is less. So, we tweak the application of our technology to the application.
Sure. But I'm trying to say, how would you create the baseline to understand if we wanted to plant? What 50 acres of the 150-acre field would we plant? And I'm looking at, can we farm a third of the field and get half the yield with a third of the water? You
Yeah.
see?
Oh, well, so what you do is you take that signature, those zones that
Hmm.
I just described, and
Right.
then you go investigate the soil attributes that exist in there. And it might be the same. I mean, from as a soil scientist,
Hmm.
a lot of times you'll have a valley and you'll have the same 5 soils repeated over and over and over again in different patterns, right? And so it's going to be the same on your example. There's going to be parts of that field that are soils that are not very productive. And until you find those and you identify those, you can't make those decisions. So going in, it might be something as simple as the thickness of one of the layers. It might be exactly the same soil as another part of the field, but the sandy loam horizon layer is thinner over here and thicker over there. And that's something that wouldn't show up in a traditional soil lab or a traditional soil measurement because it's an attribute. It's not a property. Same property, but it's thicker over here and thinner over there. Nobody, systems aren't taking that type of thing into consideration. So those go into the decision, and you would be able to tell if you have any yield maps on top of that. That's even better. But even without yield maps, you can use remote sensing historically and investigate the patterns and find out what is it that's causing it.
What areas are you most excited about today helping farmers with? I mean, we've mentioned almonds, pistachios, grapevines. What are other crops that your team's worked with and been successful with?
Well, we do focus on permanent high value crops just because that's where the low hanging fruit is. We've done kiwis, we've done vineyards, avocados, citrus.
Hmm.
So any sort of permanent crop. We're excited about our work. We just opened up a wholly owned subsidiary in Australia. We've got a lot of work that we're going to be starting there on almonds and other crops. So I'm excited about expanding back out internationally. Um, we have conversations that we're having with folks in Oman on date palms. So that's another interesting crop that we don't hear much about. There are some in California.
Hmm.
But those are a very high value crop that have a lot of management issues associated with them. So I'm excited about our expansion both geographically, but really the biggest opportunity is and the most immediate ROI are these variable rate maps,
Hmm.
right? Lime, gypsum, SOP. If you're putting a one size fits all amount on your field, you're not taking advantage of the opportunities, and you're probably spending too much and you're minimizing your potential yield.
What about other higher value crops that are not yield monitor capable? So let's say processing tomatoes, veg crops, produce crops, melons, sweet corn, those kind of things where we have higher value, but they're not and need different management accordingly. And mainly water management would be some of the big keys there.
Right.
What kind of application you see for LandScan going forward in that?
Well, so from an irrigation perspective, one of the products that we produce is the root zone plant available water.
Hmm.
And so depending on the specific crop, how deep do the roots go? What sort of agronomic research has ever been done on that crop in terms of limitations? And then you can produce the irrigation for that block. If you don't have precision irrigation, right, the ability to put more or less in different places, but you just have a one size fits all, how long am I going to run it today? Decision, we can give you that best one size fits all for that block because we know where the water actually is, where the roots are. So, you have to manage the bank of water that you're going to actually use, and it's the plant available water, right? Because not all the water in the soil is available to the plants, where the roots are. So those two things together are important for managing irrigation of any crop.
Hmm.
And it's specific to that crop and its roots and its requirements.
And again, that basically a plant available water holding capacity will be driven by what you're getting out of the probe that you're sending down to 4 feet.
That's right.
See all those
And because we're taking enough observations with that probe
Mhm.
to actually make a statistically accurate, spatially accurate map.
Long term, do you see an application in more of the commodity crops, large acre, where you do have yield monitors, and we would want to go in and say, hey, let's split this field into 5 yield zones, distribution curve, and we want to maybe isolate those really poor performing areas and figure out what's going on, or do you see more diagnostic work, or can it be whole field work based on cost of application?
I think the place to start is on the research plots, right? So if
Ah,
you're a company and you're developing drought tolerant hybrids, for example,
mhm.
and you don't know that your test plots cut across plant available water holding capacity zones, which they undoubtedly do,
Sure.
and you're pulling your data from your plots and it's different soils on different parts of the plot, and you get a 10 over here and a 2 over here, and your answer is 6, but it's not 6 anywhere, it's 10 and 2. So once you can further disaggregate, there's a lot to learn at the research. So which hybrids, for example, which pesticides, herbicides, whatever it is that you're testing on those plots,
Mhm.
start by mapping those soils. Then for recommending the best efficacy of that treatment of that product, you then want to map the soils. Because like, hey, this particular type of hybrid performs best in this soil.
Mhm.
What kind of soil do you have? Well, okay, now we need a digital twin to be installed on your field so that you have that knowledge of what the soils are on your field, and then you can make the proper recommendation. Because if there's too much noise, also
Mhm.
the research products don't get out to market quick enough because that number 6 you got, the agronomists are looking at that and going, wait a minute, that doesn't make sense. This shouldn't be like this. And so they know that there's an opportunity, but the numbers, the stats, the analytics don't bear it out because they don't have everything's too aggregated in their analysis. So I think that's how it's going to get into row crops is starting with the research so people understand how it relates to the products.
And that's a great point because there's so much noise involved in research plots as far as, we're trying to tweak out one difference, statistically, and yet there's so many other factors built into there that a lot of
Right.
times there's statistical insignificance just because those larger overarching soil factors are there.
Absolutely.
What's on the radar for the future? Where do you see all of this leading to for yourself and LandScan? What's kind of the next iterations?
Well, expanding back out to all 6 continents again. The markets that are in California, there are a few exceptions, but the world has maybe another 90% of those same acres that California represents about 8% of the global market. It's a great place to cut our teeth. A lot of the same companies grow crops in California, and they may grow them in Spain, and they might grow in Turkey. They might grow in Australia. So it's really expanding our services out to these other geographies. We're going to do that through licensing. So we're going to train local organizations to collect the data as a service, and then provide these recommendations and the analytics to their market. So that's really our focus in growing the business. And we've done this before. I think we're the only team of people in the world who have done commercial soil and remote sensing mapping on all 6 continents. So we're confident that we can pull this off again and with better technology. And it's really exciting because we've produced a new type of metrology, a new type of measurement, a new datum, a new reference for soil. And the current paradigm, the current reference is inadequate to run analytics and to expand the potential of ag tech around the world. So it's like the world before the microscope, right? I mean, once doctors had a microscope, they were able to make new discoveries and make better decisions. And so with our new way of measuring the soil and the vegetation, we're making discoveries. We're discovering relationships that we currently didn't or previously didn't realize existed. And so I'm really excited about that and how it's going to be applied for general exploration. I think the other thing that really would sort of be the main goal, and it always has been, is to change the way global soils are surveyed, right? So we have the USDA Soil Survey in the United States, which is probably the world's best natural resource database ever created. It's amazing. The amount of knowledge that's gone into that with these representative profiles. And what we can do with the digital soil core is we can go to every USDA representative profile. And they're unique because of the layers and what's in those layers, the color, the content. You can go up to any one of those and push the digital soil core in, and just the digital signature from all the sensors will allow us to distinguish each one of those from one another, right? So you work with the USDA, take us to the representative profile of the Antigo silt loam, the state soil of Wisconsin, for example. And we push it in, we map it, right? Now, anywhere in the United States, you can go and you can push the digital soil core in. Never worry about the lab. Using the lab is the old way, right? Now I can tell you which one I'm closest to and update the classifications. But even better, I can go anywhere in the world and push the digital soil core in, and immediately using the advanced generative AI, I can crawl out into all the research that's been I figure out which one I'm closest to. If I'm in Mozambique, hey, it's like that soil in Missouri. And that soil in Missouri is suitable for this and this and this and not for that. And look at all the research that's been done in the field on that soil. And you can immediately use that information to explore and prospect unknown soils. And you create this way of objectively connecting, which you can't do with subjective soil samples and error-filled labs. So the ability to change the way soils are surveyed and understood globally and to build on databases like we have here in the United States, I think that's the real home run. And that's going to take some time to make that happen. But that would be the ultimate goal.
Right. And how those were made. I mean, it's a great process that we have the soil type information we have in the United States, but it was made years ago with, flyover photos and,
Yeah.
draw the line and, sample to verify. But there's a gradient to all these things. And
Needs to be updated.
yeah,
It absolutely needs to be updated. But the knowledge that's there,
right. To
priceless.
reference A, reference B, and then you can see the gradient in between, and that'd be very powerful.
Right.
Yeah.
That's right.
How do farmers, agronomists get started? What does that look like working with your team?
Yeah, so we have on our website landscan.ai, we have a services tab, and folks can fill out the information there on where they are, what size the fields are, what type of crop, and one of our folks will reach out and start the conversation.
And does your team do the probes and those things, or is
Yeah,
that
we do all the
independent?
service.
Okay.
Yep, we do the services um, ourselves and work with the agronomists on the team so that they can understand and interact with the software. But really, once we get those requirements, as far as the variable rate, the data we produce goes right into the variable rate spreader. So it doesn't require somebody on the other end to do anything. We, of course, make that transparent, that process transparent, let them make those decisions, not us. Like we just are telling you what's there, and then the agronomists or the managers can make those decisions and interact with our software, and then the prescriptions come out and they're put in place.
So they can access a probably a cloud-based type of scenario, and they can say, "Hey, I want to, if it equals this, then 150 pounds or whatever that kind of tweaking they may want to do."
Yeah, that's right. We get their materials in our software, and the recommendations are made based on their preferences. Um, and what their yield targets are, because we then adjust the yield targets based on the potential yield on that part of the field, which is another level of optimization. Right? Because you're not getting, as you said earlier, you're not getting 3,000 pounds. You're getting anywhere from 1,700 to 4,200 pounds.
Mhm.
Right. And so that level of adjustment in the hands of an agronomist who understands what the implications are is super powerful. So
Right.
it's a really quick iterative process once we install the digital twin, and they have access to that anytime they want to make those decisions.
Very good. What other thoughts before we have to part ways today?
No, I appreciate the conversation. It's what we're doing is different,
Hmm.
and it's you could consider it disruptive, but I think it's the only way forward. And we're not selling. Talk about ag tech. We're not selling somebody a gadget or a potion or something that has to work. We're creating a digital twin of your most valuable asset, your land, and how it relates to your crop. It's not something that somebody has to figure out how to use, or it works or it doesn't work. It's something that will make everything else work better. And so that's really how I like people to think of us. And, are we in ag tech? Well, we use ag tech, but we're not selling anybody ag tech.
Yeah. Dan, what I think so amazing is not only going through the three transitions that you've been through in a company, but looking at the technology in that soil probe. That's one thing that one company could accomplish and be amazed that they accomplished that. All right. The second part is do that aerial imaging portion of it and solving for a lot of problems in there to really understand what's happening in that field. But then merging the two together, that's where the magic's at, and that it's amazing what you've accomplished over this couple decades of work that you and your team have done. It's and really, I'm not aware of anyone else out there doing it to this.
There is nobody else. There's nobody
And
else in the world that does the analytical remote sensing, the digital soil information, and therefore run the analytics. You got
yeah,
to have both of those before you run the analytics. And so it just opened up a whole world. It's
yeah.
super interesting.
Well, we'll certainly be talking more here in the future how we can use that to help farmers that we work with, and but just want to congratulate you on that vision to put those things together because that took a lot of patience, a lot of time, I'm sure a lot of capital raising, and a lot of finding the right people. Your journey as a CEO has been pretty impressive too. So,
Thank you. I have a
congratulations.
great team of people, many of whom I've worked with for more than 20 years, and couldn't do it without them, obviously. But I can't say enough about my team.
Yeah. Well, excellent. I appreciate it, sir. Thank you for all that you're doing to help farmers and really make a huge difference. Now, we just need to have everybody do it, Dan.
That's right. Well, we will. We're getting there.
Well, very good. Thanks again for your time. Have a great day, sir.
Thank you. Take care. Bye-bye.
What a cool conversation. Dan's innovative approach to soil mapping and digital twin technology is paving the way for smarter, more sustainable farming practices worldwide. A huge thank you to Dan for sharing his expertise and vision, and be sure to visit LandScan to learn more and connect with their team. And if you're as excited as we are about the future of agriculture, check out our website at asn.farm. And there you can click on links to follow us on Facebook, X, Instagram, LinkedIn, and YouTube. There's a lot of great things happening and always something to learn. Thanks for listening.